Okay, so today's lesson is about what we refer to as Vesper shapes, and I know VSEPR doesn't necessarily sound like Vesper, but it really comes down to valence shell electron pair repulsion theory. What that means is that we know that when nonmetals bond together, they're sharing electrons, and when they're sharing electrons, what ends up happening is we know that electrons are negatively charged. And if electrons are negatively charged, we also know that they don't want to be near each other. And as a result of them not wanting to be near each other, they push away from each other in three-dimensional space. Okay? So the thing of it is that valence shell electron pair repulsion theory is really the theory about the electrons in bonds to the central atom. So it's about electrons and bonds to the central atom and how they repel each other. So the atoms will arrange themselves around the central atom in a way so that they are as far apart from each other in three-dimensional space as possible. So if going back to the first practice problem from yesterday, you had like nitrogen and fluorine and hydrogen, and they were all bonded together singly, and then there was this unshared pair of electrons here. Okay. Now, in the valence shell electron pair repulsion theory, or Vesper theory, we're only concerned about the bonds and the electrons that are associated with the central atom and nothing else. So the fact that there are electrons around the fluorine here, they have very little bearing on the shape of the molecule. It's the bonds and the atom and the electrons that are on the nitrogen that are all about the shape of the molecule. So, for example, there's some nomenclature that I'm going to use that might be helpful for understanding it, especially if you're a pattern-oriented human being. A always refers to the central atom. X refers to atoms bonded to the central atom. Actually, it's number of atoms bonded to the central atom. And then E refers to number of electron pairs on the central atom. So in reality, E refers to those electrons there. X, E, that's not a great line. X refers to the electrons in these bonds here. And then A is clearly the central atom in the structure. So through experimentation, through data collection, through the way that molecules tend to stick together, we have been able to determine some very basic shapes that molecules tend to form. And there are a bunch of shapes, but we're really only going to be concerned with some of the shapes. So let's talk about a few of them. Oh, I went too fast. Let's talk about a few of them. The first shape that we're going to talk about we're going to use CO2 as our example, which happens to be carbon dioxide. And so if we do things the way we've always been doing them, we would see that there is a carbon atom and there is an oxygen atom, and we know that there is one carbon times 4 valence electrons, and there are 2 oxygen atoms times 6 valence electrons. So that's 12 valence electrons. We add that up. That's like what? 16? Yeah? Valence electrons. So I'm going to draw my structure. It's carbon and oxygen and oxygen. I'm going to bond them together singly. And I know that there's going to be multiple bonds here. I'm not going to go through that whole process. So I'm going to just bond them together and draw the structure as it is without going through the process to figure that out right now. So if you need help with that, make sure you see me. But this is our structure for carbon dioxide. Now, the number of elements bonded to the central atom, in this case, happens to be 2. It's the oxygen on the right side and the oxygen on the left side. The number of lone pairs on the central atom, or unshared pairs of electrons, happens to be 0. There are no dots on the central atom. So this structure happens to be referred to as an AX2, and that's it. There could be an E0, but I don't think I'm going to do that. Now, this structure has a very specific shape name that we call linear. This is a linear molecule, okay? It has a central atom. It has 2 atoms bonded to the central atom. And the bonds here are as far apart from each other in 3-dimensional space as they physically can be. As a matter of fact, what's the definition of an angle of a straight line in geometry? It's 180 degrees. So the bond angle from this bond all the way over to this bond is exactly 180 degrees. Because in 3-dimensional space, right, these atoms bonded to the central atom are as far apart from each other as they physically can be. So we call that linear. Okay? And in your packet, you already have a picture of this, right? Moving on. So in the next example, right, we've got NO2 minus and H2O. Now, I'm going to go ahead and calculate things for both of these. So I've got N and I've got O. I know that there is 1 N times 5 valence electrons. I know that there are 2 O's times 6 valence electrons. If we add all that business up, that's 17. I see that there is a negative sign here, so I have to add 1. So I have 18 valence electrons to find a home for. And again, in an effort to make our lives a little bit easier, I'm going to draw the structure sort of quickly here. So I'm going to draw nitrogen, and I'm going to have my oxygens attached to it, like so. And then I'm going to go ahead and put a bond here and here. So that's 2, 4, and then 6, 8, 10, 12, 14, 16. And I know that we need to have a multiple bond, so it's going to be 18. And because this is a polyatomic ion, I need to put it in brackets and put the -1 charge. Now, if we were going to assess elements and all those things bonded to the central atom, in the case of this structure, there are 2 elements bonded to the central atom, and there is 1 unshared or lone pair of electrons on the central atom. Yes?
Why is it that we put the brackets around it again?
Because in a polyatomic ion, it's a group of atoms that have a charge. And in this case, the group of atom is the N and the NO2. That whole group of atoms has a charge of -1.
And
And then why would it be 2 bonds for nitrogen when you had to do another bond for the oxygen on the left side? Wouldn't that be 3 then?
So remember we talked, so there's a couple of different ways this structure could be drawn. And we're doing the one that is the resonance structure is the best for. So in theory, you could have a double bond to both oxygen. Well, you really couldn't, because actually when you look at this, right, in order for nitrogen to be satisfied, it needs 8, and it's participating in 2 bonds and 3 bonds, which is 6, plus those 2, so that gives it 8. On the right-hand side, if you make a double bond over there on the right-hand side, the nitrogen ends up with a double bond, but then the oxygen ends up with 10. So it doesn't work out. Okay. All right. Now, going back to, so this one would be in A, X2, E1. So now we're going to do H2O. I know that the central atom is oxygen, and there are 2 hydrogens. I know that the central that there is 1 oxygen times 6 valence electrons, so that's 6 valence electrons. And there are 2 hydrogens times 1 valence electron, so that's 2 valence electrons, for a grand total of 8 valence electrons. So when I draw this structure, I'm going to put my oxygen in the middle. I'm going to put my hydrogens on either side. I'm going to put a bond 2, 4, 6, 8. Okay. Now, there are 2 atoms, 2 hydrogens, bonded to the central atom. There are 2 unshared pairs of electrons on the central atom. And so this coding scheme would be in A, X2, E2. So somebody this morning was like, why does it have eyes? I was like, what are you talking about? Why does it have eyes? And then we went back and forth for a couple of minutes, and they were like, and I realized they were talking about the structure in their packet. So it had eyes. So I drew eyes on mine. So here's my central atom. Here's 2 atoms bonded to the central atom, right? And because there's 2 atoms bonded to the central atom, and they're an unshared pair of electrons on top, that unshared pair of electrons. So here's the thing. Instead of being linear like the last one, right, this unshared pair of electrons on the top is so negative that it's creating a lot of negative space on top of negatively charged space on top of this central atom. And as a result of that negatively charged space, it forces the negative electrons in the bond to bend down a little bit. So it creates this structure where instead of being a flat line or a straight line, it's more of a ee-oo. In this particular structure, we call a bent molecule. Well, yeah. So like here, I have the other structure. So I have an oxygen, right? And I have 2 hydrogens, right? And I've got 2 unshared pairs of electrons here. And these 2 unshared pairs of electrons are creating a lot of negatively charged space up here, right? And as a result of that, they are pushing away from each other, but they're also pushing these structures down. And when they're pushing these structures down, instead of being straight, there's a, that's the shape that makes, right? And so now we have another version of the bent molecule. Does that make sense?
Yeah.
Don't slip. It's water. Classic chemistry joke. We good? We good? All right. Next couple here. You want to pick up my water? Thank you. I appreciate it a lot. Okay, so now we have a linear molecule. We got a couple of bent molecules. Now we need to get into some really, 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 really important things. So in this next structure here, I have carbon and I have oxygen. And I have 1 carbon atom times 4 valence electrons. So that's my 4 valence electrons. I have 3 oxygen atoms times 6 valence electrons. So that's 18 valence electrons. I believe that adds up to 22 valence electrons, but there's a negative 2 over here, so that means I have to add 2. So I end up with 24 valence electrons that we need to find a home for. So we're going to take our central atom, which is carbon. To the central atom, we are going to bond oxygen and oxygen and oxygen. We're going to do it with a single bond, single bond, single bond. We're then going to go and add our electrons around. So at this point, including the double bond I'm about to put in here, I've used all 24 electrons. And some of you might be saying to yourselves, V, if it's got a double bond there, shouldn't there be like resonance structures? And the answer to your question is 100% absolutely. There should be another structure where there's a double bond pointing down and another structure where there's a double bond pointing to the left, right? But for the sake of this lesson, we're really focusing on the shape made by this molecule. So in this case here, the number of atoms that are bonded to the central atom happens to be 3. There are no unshared pairs of electrons on this one. So I'm going to call this structure in AX3. Okay. This is an AX3 molecule, okay? It is one central atom with 3 atoms bonded to the central atom. And if I hold it this way, hopefully what you can see is that all of the bonds appear to be in the same geometric plane, okay? And as a result of them being in the same geometric plane, that means that these bonds are as far apart from each other as they physically can be in the same flat plane. And this has a very special name, and that special name is Trigonal Planar. And I know some of you are going to be like, trigonal, and I'm going to want to yell at you and say, no, that's not appropriate. Because what's the math class you take? AAT, what's that called? And trigonometry, not trigonometry. So it's trigonal. See what I did there? No. The next time you do that, I'm going to take points off your final assessment. Whoa. Keeping track.
Trigonal.
There you go.
Who's James and why?
Don't worry about it. He said it a bunch of times, and he learned. So for those of you that are playing along at home, on my board, I have a human's name and a -4 next to it because that human said trigonal instead of trigonal 4 times.
Would they not be a human? Why did you specify they're human?
They're definitely a human. All right.
That's sus, man.
Next one. I don't know if that's really all that sus. So we have nitrogen. We have hydrogen. There's 1 nitrogen times 5 valence electrons. There is 3 hydrogens times 1 valence electron. We add that up, we get 8 valence electrons total. So in this scenario, I'm going to take my central atom, which is nitrogen. I'm going to add my hydrogens to it. I'm going to bond them together with a single bond, 2, 4, 6, 8. So in this instance, I have 3 atoms bonded to the central atom. I have 1 pair of electrons, lone pairs or unshared pairs of electrons. So I would denote this to be an AX3 E1. Looks like this. So here's my central atom. Here are the 1, 2, 3 atoms bonded to the central atom. And then here's that negatively charged space on top because there's 2 electrons up there. These 2 electrons up here are creating a lot of negatively charged space on top. And as a result of that, they're taking the electrons that are bonded to the central atom and pushing them down. So if this is trigonal planar, all in one plane, this is trigonal, and it happens to look like the shape of a pyramid in 3-dimensional space. So this is referred to as trigonal pyramidal. Careful what you say. Trigonal pyramidal. Nope.
Oh no.
Yeah, right. Trigonal. So this is our shape, right? Questions about this? All right, we have one more shape we're going to cover today, and then you will have no homework tonight.
Yay.
I know. I feel bad about it. I feel like we should practice our craft every day and not take a day off.
Oh, you were in the orchestra with the very nice melody.
All right, so here's our structure. I've got 1 carbon times 4 valence electrons, 4 hydrogens times 1 valence electron for 8 valence electrons. I'm going to take my carbon, put it in my middle. I'm going to attach my hydrogens to it. And I've got 8, so it's going to be 2, 4, 6, 8. Number of elements bonded to the central atom would be 4. Number of unshared or lone pairs on the central atom would be 0. And so this one is going to be simply referred to as an AX4. This one looks like this. It has a central atom. It has 1, 2, 3, 4 atoms bonded to the central atom. And if you can tell that they're like, no matter how I turn it, there's always like one atom pointing up and other atoms seem to be pointing down. But there is 3-dimensional space in between each of these that's the same. Like technically this angle from this bond to this bond, like here, is 109.5 degrees. It's always the same. So, but you don't need to know that. You just need to know that an atom with a central a structure with a central atom with 4 atoms bonded to it, that's all, has a very special name, and that very special name is tetrahedral. It is tetrahedral. So those are the structures that we talked about today. We'll cover the remaining structures in class tomorrow. If you have any questions, let me know. Otherwise, enjoy the lack of homework